Alright, hell yeah. So what we have here is a hinged bar, and what we're going to kind of derive is the equation of torque, and we're going to do this. We're going to be like, hey, the sum of the torques is equal to I alpha. And we're going to explain that in terms of linear motion, you know what I mean? So hell yeah. So the easiest way to do that, and the first step, is to take this bar and pretend it's massless, and then put the mass right at the end. Okay, so this bar has a length L, and then we have some sort of mass right at the end of this. So we have mg. Okay, sweet. And so now we can use our equations, specifically the moments. We want to know what the moment about point O would be. So we're going to sum the moments about point O, and if they're not equal, then what are they going to equal? You know what I mean? Because we have the definition of a moment is force times distance, and so if we have Newton's law that force is equal to mass times acceleration. So if we do generate, if the moments are equal to something and they're not equal to 0, then they're going to be equal to some sort of force times distance, and that's going to be equal to mass times acceleration times distance. And this really only works if you're doing kind of a linear in a linear fashion. All right, but let's do it. So we're going to sum the moments about point O, and we see that we have a force that's a length L away. So our force is going to be mg, and then the distance to that force generating that moment is L. Cool. So oh, and I kind of have this equation written wrong. Kind of the generic form in a linear fashion would be the sum of the moments is equal to the mass times acceleration times the distance to wherever that mass is. But this has to be a point mass, and it has to be away from, you know, the point that you're taking it. So this mass has to be a point mass, but you can find the linear acceleration of that point as long as it's a, you know, and then it's a distance away from that. So so hell yeah. So let's sum. So now we just do it. So this side is we're finding the moments, and then that's going to equal to that mass times its acceleration times the distance away. And so we just found the moment. It was mgl, but that's this side of the equation. Cool. And that's going to equal whatever our particle in linear motion is going to be, mass times acceleration times the distance away from it. And that distance is L. So essentially we have mgl is equal to sorry, holy Toledo. This acceleration, it's important because this is the acceleration that you're trying to find. And it just happens to be that that acceleration will be g, but holy Toledo. So we got mgl is equal to mass acceleration L. Oof. So, and now we can, you know, lop off the masses on both sides, lop off the lengths, and we can see that our acceleration is, the acceleration of this penny, if it's on a massless rod, will fall just like it's in free fall. There's nothing preventing it. Yeah, this is kind of interesting. Alright, sweet. So now what we're going to do is we're going to chop up we got some double-sided tape. I don't think I needed that. Alright, so what we're going to do is we're going to chop this bar up into pieces. And, I mean, the first piece that we could chop it up is just right, like as is. We're going to say, hey, this bar we're going to, we're just basically going to have its mass in the middle. You know what I mean? Kind of like, hey, this bar can be represented by just a mass in the middle. And then the next thing we're going to do is we're going to say this bar is 2 masses. And you can see that if we apply 3 and then keep spacing them out and apply 4, we'll probably get to here and maybe up to 8. But you can now see that the bar almost looks like a full bar. Okay, so hell yeah. So let's just do the mass in the middle. And this is representative now of our problem. So what I guess to say what we did here, this is not representative of our problem. Having all the mass way out here at this very point, well, we have a bar that has mass throughout, so that's not a very good representative place to put all the mass. Now we know that a bar has a center of mass right in the middle, so that is a very good representative place to put the mass. Okay, so now we have this distance being L divided by 2, and we can kind of do that same process. We're going to sum the moments about O, and that should be in linear form. It should be mass times acceleration times distance. We see that this penny has a mass of mg, and so and it's a distance L divided by 2. So we're going to have that force of mg times a distance of L divided by 2. That's going to equal our mass, which is just the m, the acceleration that we want to find, and the distance away. So that's going to be mass, the acceleration that we want to find, and the distance away is going to be L divided by 2. So you can see right here kind of that same scenario. Our acceleration for this scenario is g. So, and it's kind of interesting because you know that a bar, the middle of the bar, well, I don't know if you do know this, but if you hinge a bar like this end goes hella fast. Alright, so this end will fall faster than gravity, so if you actually put a penny on a ruler, you know what I mean, and then drop one end, the ruler will fall faster than the penny, and then those will separate. The middle point of this bar doesn't fall with, it falls with less. So there's some point where this bar does fall with gravity. Okay, so we'll get to that though. Alright, so then, so we did that one. So the next place that we're going to do, we're going to chop this bar up into 2 chunks. And we're going to put the mass right there. So now these chunks of mass are at L divided by 4. And this one is going to be all the way at 3/4 L. So here's L divided by 4, here's another L divided by 4. We have 3 L divided by 4s. So that's the total distance to that. Okay, so let's sum the moments about O. And we're going to have 2 different moments. And here's our generic equation for linear. So the moment of this one, and now we're going to say that these 2 pennies represent the total mass. So each penny represents m divided by 2, or 1/2 the total mass. So the mass total is just m, and then 1/2 the mass is going to be this m divided by 2. Alright, so we're going to have the torque, the moment due to this penny, about point O, will be its mass. So we have 1/2 mg. I mean, it'll be the force, so it'll be the mass times gravity. So we got 1/2 mg times the distance. So we're going to have 1/4 L. Okay, so that's the moment there. And I'm just going to say all these moments are positive, you know, because we only have, the moments are only going in one direction. And we know that, and I'm going to say the acceleration is positive. So this is going to be my positive x direction. Cool. Alright, so, and then this, this penny has a mass of 1/2, I mean, it has a force, it's got a mass of 1/2 m. The force is mass times gravity, so 1/2 m times g, and it's the moment on it, force times distance, is going to be at a distance of 3/4 L. Cool, and that's going to equal, but now we don't, alright, hell yeah, so this is probably the hardest part, but we know the acceleration of these 2 pennies are going to be different. You know, from observation, the acceleration of this end is going to be hella high, the acceleration of this end is going to be 0. So we kind of have, that's the definition of angular acceleration. If we have angular acceleration, if we know how fast in radians, or, you know, by angle this thing is accelerating, you know, changing its changing it. Like right now it has angular speed of 0, and then in 1 second, if we have some sort of angular acceleration, the angular acceleration after 1 second will be some number. And so it'll go from 0 to you know, some number in radians per second. And that's angular acceleration. If you wanted to find, just like if you wanted to find tangential velocity, if we knew what our angular speed was, you would do angular speed times, you would do angular speed divided by, what would you do? Oh yeah, you would do radians times radius is something normal, so you would do angular speed times radius, and that's going to give you the tangential velocity. So you can see that if angular speed is tangential velocity divided by the radius, which is the same thing over here, angular acceleration is just normal acceleration divided by the radius. So if we wanted to find the normal acceleration, I mean the tangential acceleration at each of these points, tangential acceleration is angular acceleration times the radius. All right, hell yeah. So let's work through this. So here's the moments due to each of these masses, and they're and they have the form mass, gravity, distance. But now we're going to say that's equal to you know what I mean, the mass of this one, 1/2 m times its acceleration times its distance, which is still 1/4 L. So it seems like we're just rewriting it. So why would we get anything different than G? You know, that's kind of an interesting question. So now we have the force on this one, or the mass on this one, is 1/2 m. The acceleration is what we're trying to find, and its distance away is 3/4 L. And, I mean, this even trips me out. It's just like right off the bat, well, why couldn't this just be G and this be G? Well, we know if they're both falling at the same time, yeah, if we don't have a hinge here and we just have a bar falling out of the sky, yes, these will both be G. But we know that's not going to be the case, so we have this constraint that this acceleration is going to be hella, and this is going to be much less. But it is going to be proportional due to this. You know, like I said, this point out here is going to have the most acceleration. This acceleration of this point is going to be 0. And we have a linear scale. So it shouldn't be too hard. And I'll show you the way that I did it. Well, I was about to show you the way that I did it. And that might be for another video. But it's just fascinating because I don't stumble across the equation. I mean, just the fact that we can actually put the acceleration in here. You know, each of these has a different radius. So we could put alpha and then r, you know, out to this one. And that's the radius of the first penny. And then we could put alpha r, radius of the second penny. So right here we could put alpha. The distance is going to be 1/4 L. And then here we're going to put alpha, and the distance is going to be 3/4 L. Okay, but let's, and you can obviously see, I mean, we should just solve this. And then let me go show you the way that I just did kind of a guess and check method. Alright, so let's add these up. So if you see that these two terms are the same, we're going to have a 1/4 L plus a 3/4 L. So that's just going to be, so we're going to have 1/2 mgl over here. And you can see that this torque is the same. So we're setting up the problem the same every time. It's the same as having all the mass right in the center. That generates a torque of 1/2 mg, a torque of all the mass, that's the force, mg, times 1/2 L is the distance to that mass. So mg 1/2 L is the same thing as 1/2 mgl. Alright, booyah. Alright, so what we need is, like, this is the size of the torque on here. It's the size of the generating moment. The moment is being put into, you know, it's trying to make these masses being put into motion. And so And if we just had one mass, you could just see, well, yeah, the acceleration would be 0. But if we have two masses, we know their accelerations are not equal. So then we have to figure out, well, how are they different? And they're proportionally different because tangential acceleration is angular acceleration times the radius, whereas the tangential acceleration right there is 0, and here it's going to be max. Okay, so so over here, let's get all the fractions out front. So we're going to have 1/2, 1/4, and then 1/4. And then we have m, angular acceleration, and then length. Now over here we're going to have 1/2, 3/4, and 3/4 mass, angular acceleration, length. So this is going to equal 1/2 mgl. And now we can still lop off stuff. We can lop off the masses and the lengths. We're going to get angular acceleration in terms of g. We can lop off one of the halves on both sides. So let's simplify this. G is going to be, and I'm just going to do 1/16 alpha plus, and this is going to be 9/16 alpha. So that's all I did, is I just multiplied those two together, multiplied those two together. Okay, so we're going to have 10/16. That's going to be 5/8. All right, so this is still it's its own problem. It's closer to a bar. You know, I mean, we have two masses on a massless rod, so it's a rigid structure. They have to move together. They're not connected by a string. They're actually connected by a massless rod. So you can imagine this whole bar is made out of foam, and then you have significantly heavier masses attached at these two locations, and that's going to be the total mass of that bar. And we get an acceleration of 5 divided by 8. So our acceleration is 0.625 alpha. Now, if you've done the bar problem, you will know that. Oh, and what did we just? Oh, yeah. Sorry, we're trying to solve for alpha. Okay, so angular acceleration is 8/5 g. Okay, yeah, that's going to make more sense. Okay, so our angular acceleration is going to be 8/5 g. 8 divided by 5 is going to be 1.6. All right, hell yeah. And if you've done this problem, we know that the angular acceleration of a bar, you know, with length L, is going to be 1.5 g. So this approximation, even just with two with two masses, is actually getting pretty close. Because what did we say? If we said we had one mass, didn't we say we had tangential acceleration was going to be gravity. And then, so how do we relate tangential? How do we get to angular acceleration? Well, angular acceleration is tangential acceleration divided by the radius. So this would be g divided by L divided by 2, which would be 2g. 2gl. Oh, am I missing an L term here? Yeah, I think I am. Yep. Because we said this radius was 1/4 L. I apologize about this. So we have another L term in here, and then we're going to have, yeah, holy Toledo. But that's good to make mistakes. So we're going to, so we can only cancel out one of the L's, so we're still going to have an L over here. We're going to have 5/8 alpha L, and we want to get this in terms of alpha, so we're going to have 8/5 g divided by L. So there you go. So angular acceleration for this is going to be 8/5 g divided by L. Cool. And then we could, yeah, in this setup. Alright, hell yeah. And, you know what I mean, this is the first time doing this video, you know what I mean. I kind of got it down last night, but man, making a video on it's kind of difficult. So now what I'm going to do is, I'm going to do this. Yeah, no, we're good. Yeah, this is just kind of tricky. Alright, so we're going to divvy up, we're going to same places. You know, these are going to be L divided by 4. And there you go. So we got L divided by 4, 2 masses. We know that the sum of the moments about O are going to be equal to an equivalent mass times an acceleration times a distance in a linear form. But this is only if you have one mass. We don't have one mass. We got 2 masses. Okay, so but we can at least sum the moments about point O. So we have and these both pennies are going to represent the total mass. So this is 1/2 m, and this is 1/2 m. Moment is force times distance. So the force on this is going to be 1/2 mg. The distance out here is going to be 1/4 L. Cool. And that's the other torque is going to be 1/2 mg, and we're at a distance of 3/4 L. You know what I mean? 3/4. Sweet. Alright, so that's going to be the moment, and now this has to equal well, I guess let's just write it again. The mass of this one is just going to be 1/2, and then it's times the acceleration. I'm just going to say the acceleration of 1 times the distance to 1 is 1/4 L, plus we got 1/2, the acceleration of that penny, times its distance is 3/4 L. Cool. But we know that the acceleration of this penny is not the acceleration of that penny. And so what I did was, yeah, I'll go through the whole process. So I just assumed that if I was dropping both pennies for like 1 second in free fall, they would both go 5 meters. So I kind of just draw that in. And let's say, you know, this is a really long bar. So booyah, it just dropped 5 meters. And then that one dropped 5 meters. But I know due to continuity, these have to be in line. So if I draw a line through here, it doesn't intercept that one. And if I draw a line through there, it doesn't intercept. So due to being a rigid body, these two always have to be in line. So then I'm just gonna guess. I'm gonna say instead of falling 5 meters, I'm just gonna guess kind of somewhere in between. So I'm gonna guess that this fell 10 meters, and if this fell, well, and it's gonna be that we have 3 segments here. So I'm going to say this fell 9 meters, and then this one fell 3 meters. Cool. And now I'm going to use what I know about linear motion. So yeah, this is probably a horrible video, but this is how you learn. You know, you just kind of go for it. Let's see. Oh yeah. So let's say gravity is 10. And then we jump off a cliff, you know, into some water. And if gravity is 10, and let's say, and this is I always do a 20-meter cliff because it's going to take 2 seconds to hit the water. In the first seconds, you're only going to go 5 meters, and we're going to explore that. Okay, so if you jump off a cliff in 1 second, because your acceleration is 10, and the units on here are 10 meters per second squared, I wouldn't write it like that. I would say it's 10 meters per second, and even write a 1 below it, because then you can be like, yeah, in 1 second, and then I know my velocity is 0. So in 1 second, I'm going to increase, and this is kind of, you know, acceleration is a change in velocity given, you know, that change in time of 1 second. Cool. So I'm going to go from 0 to 10 meters per second. But this is where you have to figure out kind of what your average velocity is, because it wasn't like I was going 10 meters per second for this whole second. If I was, I would travel 10 meters. But if I was going 0 meters per second for a second, I would travel 0 meters. So we need to get the average velocity, so we got 5 meters per second is our average. Cool, so that's how we know we go 5 meters. And this value, if I say I fall, and in 1 second I'm traveling 5 meters, you know what I mean? So now I just have a number for the distance I traveled per in 1 second. That literally, the only way that can happen is if my acceleration was 10. So this is how I kind of like to learn. Like, move forward through something you do know, and just know that you could move backwards. So to move backwards, I could be like, well, I didn't fall 5 meters. Let's say I'm on a different planet now, and I only fell 3 meters in 1 second. So now I'm here. So I know my initial velocity would be 0. What would be my velocity right here to get me 3 meters? So this is where you have to like take a pause, be like, well, I didn't just initially use this 10 to get to 5. I said I used both of these. I said my velocity was 0 to 10, and I needed to find an average velocity. So that's going to be the link right there. So same thing here. What would be, so if I fell, so this is 0 seconds, and this is a time of 1 second. What would be my average velocity to get 3 meters? Well, my average velocity would be 3 meters per second. Cool. So now if my average velocity is 3 meters per second and I start out at 0, what would be my final speed to make an average velocity? Well, it has to be 6. It has to be double that. Because the way to find average velocity is adding your initial velocity. So we'd have 0 plus 6 divided by 2. And that gives us 3. And it's kind of interesting. Like this equation gets so I swear I graduated not knowing how to average, two different things. And this is the most important part about, kind of engineering, especially, when you're not just, you know that there is an equation to use. But what you're trying to do is kind of break it up into smaller chunks, and hopefully things are linear. Sometimes they're not. But as long as you're small chunks, like just 1 second, hey, things are fairly linear. And in this case, they're perfectly linear. But yeah, this equation to find the average. Hey, what's the middle? If you have numbers on a number line, we'll just do this. What's the midpoint between 0 and 1? Well, you would do 0 plus 1 divided by 2. That's the equation to do that. That's going to be 1/2. So what's the midpoint between 2 and 3? You would go 2 plus 3 divided by 2. So that's going to be 5/2, or that's going to be 2.5. Cool. So just a very overlooked an equation, but very useful. Okay, let's go back to this. So now we wanted to know on this new planet what our acceleration would be. Acceleration definitionally is change in velocity, change in time. I would write it like this. You could also write it in like the differential form. A very, very small change in velocity, very, very small change in time. But this still applies, especially for falling things. You choose 1 second, hell yeah, you can find your acceleration. And acceleration for falling things, this is a constant, so you're going to be 100% accurate. But just know that even if your acceleration is, constantly changing, you can still just take, like, for some problems, it's just like, hey, just take a small change in time. Sometimes you have to take 1,000th of a second, but that'll get you, that can make your acceleration. Between the acceleration in 0 seconds to 1,000th of a second, well, I don't know. Your acceleration still will change. But anyway, let's get back to this. So the definition of acceleration is change in velocity. We went from 0 to 6 meters per second. So we had a change in velocity of 6 meters per second, and we did that in 1 second. So that's the cool thing about following problems, is you can do things in 1 second intervals and kind of make the problem make sense. But like I said, let's say you had a change in 6 meters per second, but you did that in 1,000th of a second. Holy hell! You would have an acceleration of of 6,000 meters per second every second. You know, if you already did 6 in a thousandth of a second, well, you have 1,000 thousandths in a second. So your acceleration in 1 second would be 6,000 meters per second. You know what I mean? So, so just keep that in mind. All right, hell yeah. So now we're on a roll because due to continuity, we said that this was going to be 9 meters, this was going to be 3 meters. Let's do the same thing for this one. So we fell off a cliff. In 1 second, we went 9 meters. Now we need to find our acceleration. So yeah, let's do that same process. So we know that our average velocity has to be 9 meters per second. We went from a velocity of 0. We must have gone to a velocity of 18. Our acceleration must be change in velocity, change in time. So our acceleration here would be 18. Cool. So our acceleration right here is going to be 6. And our acceleration right here is going to be 18. Now this is just a total guess. You know, we don't know if we did it right at all. But let's throw them in and see if these numbers, because what we're saying here is that we have a number for the torque, and if we have these two moving with an acceleration, that's also going to be equivalent, because we did the one where we just have a massless rod with a mass. This generates a torque. And it's total linear motion. You know what I mean? It's just the mass times the acceleration times the length. And so the torque is equal to MAD. But here we just have two different things, and then we have a continuity between these accelerations. So yeah, again, these accelerations are not equal, and they're not equal to gravity. Because if they were, we would have a free-falling object. But that's the only continuity here. And so we're just using kind of the guess and check. But at the end of the day, this side, the number on this side has to equal the number on that side. It's not going to equal the number because I don't think I chose right. But let's do this. So we're going to have... Alright, so, and I can break this up. I can say that we both have a 1/2 mg, and then I have a 1/4 plus a 3/4. So it's going to be 1/2 mgl. Right, so we have 1/2 mgl on this side. That's going to be the number on this side. And if we actually want to put a number to it, we could say our mass is 1 kilogram, our length is 1 meter, and our gravity is 10. So let's do that. So we have 1/2 1 times 10 times 1, and this gives us 5. So that's what I did to solve this. And I'm just going through that's what I really wanted to do. I just wanted to go through all the motions that I went through yesterday, because yesterday I did not know how to like visualize these problems with linear motion. You know what I mean? Using this moment equation and the mass times acceleration in a tangential or a linear fashion. You know what I mean? Because right off the bat, these things are moving linearly. You know, you could say that this beam is like 100 meters. That's what I kind of visualize. 100 meter long, and yeah, this thing is just sweeping out 9 meters and 3 meters. That is a very linear distance. Now it's going to be curved a little bit, but you can put that to side. You know, as long as this distance is really large, you could make this 1,000 meters, and then yeah, 9 meters is just nothing. Cool. All right, so. And it's still representative of what this might do in 1 second, because you know free-falling objects will move 5 meters. So hell yeah, this could move 9 meters and 3 meters, but to sweep out a very small angle, if this is going to be 9 meters and the angle is going to be, you know, kind of visually representative, well, this would have to be quite long. So hopefully you can kind of see that. Okay, so, but we have a number on this side. So the moment, it has to be 5, and then we're going to add the moments over here. And so let's see what we have in common. Anyway, I don't think we need to do that. So we have 1/2. We found the acceleration on this. It was 6. So we have 1/2 times 6, 1/4 times 1 plus 1/2 times 18, 3/4, and then the length is just 1. Cool. So so we're going to have 3 divided by 4, and then we're going to have 9, 9 times 3, 27 divided by 4. So we're going to have 30/4. Okay, so 30/4, is that close to 5? 30 divided by 4. That's 7.5. Okay, so this is what I did. I was just like, well, this side was too high. So I need to reduce this number. And so let's make this number like 6. And then we're going to make this number 2. You know what I mean? And then just know that, I guess I didn't spell it out, is that due to continuity, you know, you have similar triangles here. Or, you know, yeah, so you have three segments. So if this segment drops 6 meters, you know, this is going to drop 4, this is going to drop 2, and this is going to drop 0. So it's a linear relationship to get out here. So now we're actually going to start to get equations. So what did we do here to actually get acceleration? I mean, one thing is just like, well, if I said my distance was 5, what was my acceleration here? That was 10. Oh, okay. And then, you know, so that's one way. If I said my distance here was 3, what was my acceleration? It was 6. Oh, okay. So isn't that just multiply by 2? 5 multiplied by 2 is 10. And then how about this one? What was my distance here? 9, and my acceleration was 18. So yeah, so you could just say multiply by 2, but you kind of want to go through all the different steps, and you can kind of derive the kinematic equation. And it's a good way to do it. So let's do this. So we're going to say we're going to drop 6 meters. And now let's run through this. So our little object drops the 6 meters. And so yeah, so we have a velocity of 0. We know our average velocity has to be 6. We know this velocity, our max velocity, has to be 12. And then we know we have a change in velocity of 12. We have a change in time of 1. And so, what did we do to all those numbers? If we inputted this number at 6, and then we inputted a change in time of 1, those are the only two parameters that we said. We said in 1 second we're going to go 6 meters. And we started with 0 velocity. So now I'm probably overcomplicating it, and I actually didn't do it that much. I just said, well, how did I get from 6 to 12? You know, what were the steps? Well, I took 6, and then I had to multiply by 2. 6 times 2 was going to give me that max velocity. 12. And I just knew that because my velocity was 0, that max velocity is my change in velocity. So this is equivalent to change in velocity. And that was it. So I just so that's how I visualized this problem yesterday. I just said, hell yeah, I just had 6. For whatever my distance input was, I'm just going to multiply by 2. And that was the equation. That's the equation that I used. But if you go through all the steps, and let's go through it, well, actually, I really don't want to. But yeah, the kinematic equations, you start with acceleration is 10, and then you know that this is dv dt. That's the definition of acceleration, change in velocity, change in time. That's why I would also write it like this, change in velocity, change in time. Because if this number is a constant, then hell yeah, this equation jives. It's 100% useful. But we do have this differential equation, and so you have to split up your variables, and then integrate, and you get velocity is 10t. Cool. And then you know that's change in position, change in time. And you separate variables again, you get position is going to be 5t squared. You know what I mean? Your t, integrating 10t to the 1 goes to 10t to the 1 plus 1 divided by 1 plus 1. That's using, the power rule of integration. And so we would have 10t squared divided by 2, which is 5t squared. So this is the equation that I'm using to get, and then right here you're just like, well, what is this 5? This 5 is, the general form of this is position is acceleration divided by 2 times t squared. So you will see it like this, 1/2 at squared. So if I say I fall a distance of 6 meters in 1 second, I can solve for what my acceleration is. So I would say 6 meters is equal to 1/2 acceleration times 1 squared. So I can see that my acceleration has to be double. So we have 6 is equal to 1/2 times 12. And that'll give me the acceleration of 12. So that's why I just know to run it for 1 second, because my change in time isn't going to get exponential on me. If I run this thing for 2 seconds, well, yeah, then you have it's going to be more math. But if you just run it for 1 second, this t squared, just basically drops out, and you have position is equal to 1/2 times acceleration. So that is literally the equation that I used the other day. All right, hell yeah. So let's clean this up and see if we can kind of do it again. So we're gonna divvy this up into 4 chunks. We're going to have it fall for 1 second, and we're basically just calling this a linear distance. And so now we're at the point where, well, this mass is 1/2 m, and this is 1/2 m. L divided by 4, and these are all L divided by 4. So this distance is 3/4 L. To get up to speed, some of the moments about this are equal to MAD. And we're trying to do this. The whole idea of this video is to get torque related to linear acceleration, and then see how that applies, because we know that the sum of the torques is equal to I alpha. That's the same thing as sum of the moments is equal to I alpha. So it's this I alpha term that I'm not even going to go into it actually today, of the mass moment of inertia, this I term. We can solve for alpha. So we've done that. We've solved for alpha using this equation, using a linear representation of what's happening. So that's the most important thing, because if someone that's the whole reason for trying to do this video, is because if I get this equation that torque is equal to I alpha, I don't believe you. You know what I mean? And I just don't want to use an equation that I don't know where things are coming from. And I think it's really cool, especially in Newtonian mechanics, that you can still relate things to linear motion. That's all this term is. This term represents, hey, if you have a circle, well, yeah, if you have a disk of stuff, and it's spinning, yeah, all your masses has a tangential velocity, and then so this term is actually pretty easy to find. But if you have a disk like this that's rotating, well, now I have masses that have different velocities. This tangential velocity is way bigger than that tangential velocity. So a little motion, if I go from 0 to, start to accelerate this thing with a torque, like, hey, all these masses are their change in velocities are going to be very different. So then I would want to be like, well, what's the average change in velocity? And we're basically doing the same thing. It's just like, well, what's the average? And what we're relating is the constraint that these two things, so we're going to say this is 6 meters and this is 2 meters now. So we're going to run through this one time, but then what we want to get to, we want to basically just change this into a variable. We're just guessing. And so this is the other way to do it, is just like, this is why guessing works so well. And it's the reason that we guessed 3 times on this and then kind of came up with the kinematic equation, which is always a smart thing to do. Just kind of like, run through the motions of what the kinematic equation does, and then see that, oh, it is an equation unto itself. And so that's the same thing we're going to be doing. So we're going to guess this again. Let's start with our torques. We're going to have the force. So moment is force times distance. So we're going to have the force on this is going to be 1/2. And I am going to pause because we do have an Earth underneath us. And where are we getting this force? Why are we saying that the force is just mass times gravity? And in our case, for each of these individual ones, 1/2 mg. You know what I mean? This is where I think physics teachers, like why do they just teach it once and then stop teaching it? You have this force. This is a force of gravity. You have identified a mass. And why do you have a force right there? Why do you have a force of gravity? It's because you have a huge Earth underneath and you have a chunk of mass, and those two things want to come together. And you can prevent them from moving, but you actually have to support this chunk of mass at the same amount that the Earth wants to be attracted to that mass. It's kind of like a magnetic attraction. But the equation for that attraction, that force of gravity, is gravitational constant, this mass, times the mass of the Earth divided by the radius of the Earth squared. Now in this equation, this is constant, mass of the Earth don't change, and everything that we do in physics happens between sea level and Mount Everest, and that distance between sea level and Everest does not change this value. This value is 6.73 times 10, did I say that right? Times 10 to the 6, who cares? But it's basically 6, no, it's 6.2, it's 6.27. Yeah, I don't, yeah, it's 6 million meters, you know what I mean? That's why sometimes your memorization skills can get off. That's why we just, you want to memorize things in like 3 different ways. The who cares method, this is 6 million meters. Cool, that's really good to know. I mean, yeah, I just think the devil. Like, this is 6.66 times 10 to the, you might not know, but the mass of the Earth is it 6? Yeah, there's 6's in everything, but it's 6 times 10 to the, hey, you might not know that. Radius of the Earth, though, is 6 times 10 to the 6. So, you know what I mean? I do this, and if you wanted to figure out what the gravitational constant is and the mass of the Earth is, well, I think you would need to at least remember one of these. But this one's 24 and this one's -11. And if you do the math on this, hey, oh, and this term is squared. So this becomes 6 times 6. These 6's cancel. This goes to 10 to the 12. When you divide by 10 to the 11, I mean, when you multiply by 10 to the 11, that's the same thing as 10 to the 11 downstairs. That's 10 to the 23, and then you're going to have 10 to the 24 upstairs. So 10 to the 24 divided by 10 to the 23 is 10. That is, these 3 numbers are gravity. And you know what I mean? And I think, like, this is, I don't know, I really enjoy that type of proof. I don't know. I mean, using some memorization, throw in the Illuminati at it, and then you can, like, look how many 6's there are. I mean, this is 6.67, but still, 666, holy hell, you know what I mean? And then you have 6 times 10 to the 6, and then you square it, and then you have 6, and then the only other 2 numbers you have to remember are -11 and 24. I think you should be able to memorize 24 for the mass of the Earth. I mean, it's not 22, it's not an odd number, it's not 25 or 23, it's not 26, so it's 24, you know what I mean? So there you go. Alright, but that whole show was just to show you that the force of gravity was this number 10 times the mass. So we have 10, and this is in units of meters per second, squared, and then you have the masses in kilograms. And that's going to give you newtons. So definitionally, 1 newton is 1 kilogram times meters per second squared. All right, holy hell. So now where were we? Yeah, we're just trying to find the moment. So that's why we have the moment is this force times that distance. So that force is, hell yeah, 1/2 mg. So now you know where that g comes from. And now you know why you just multiply the mass times the g. It's this equation right there. Yeah, this mass would be your 1/2 m. And then this would be your g. Cool. Alright, so 1/2, and then, so this is the force times distance. The distance is L divided by 4. I guess I'll just write it like that. And then we have another one, 1/2 mg, and that distance is 3/4 L. Cool. So this gives us the number 1/2 mgl. And if we throw in mass of 1, length of 1, this is 10, that gives us that number 5. So that's kind of what we're shooting for. Okay, so this is going to equal mass, the acceleration of our first one, times the distance to our first one. I'm just going to write it like that. So now you can just see that we're using a linear, linear equation for acceleration. But we just know that a1 cannot equal a2. And we just guessed, and this is the constraint that we guessed. So we're going to say we're going to have 1/2 m. This distance is going to be 2. Oh, so my bad. If this distance is 2, so we needed that equation. So we're saying this, and let's get to it. So I'm going to say this distance is x. So we take x and then multiply it by 2, and this gives us our acceleration, because in the next iteration of this I'll use this equation. So we wanted to find the acceleration of this point. We didn't know it, but we knew the distance. So that's just going to be 2 times 2 meters. Cool. And I'm going to drop the meters because that'll confuse that with that m. Okay, so that's it. Or no, that was the acceleration term, and then the distance is 1/4 L. Alright, so this term is going to be 1/2 m. That's going to be our mass. Our acceleration is going to be 2. Oh, and then I guess we'll just get to it, is just like for the next iteration, I'm going to call this x. And if this is 2, what is this? Because we have these 3 chunks here, and this is 2 meters, this would be 4 meters, this would be 6 meters. Well, this chunk would be 3x. Cool. And so that's going to be the distance. And then the acceleration of that would be 3x times 2. So this one is going to be x times 2 for the acceleration. So I'll write it like that, x times 2. And then this one's going to be 3x times 2. So we're going to have 3, that x value is 2, and then times 2. And then we're going to have this distance away at 3/4 L. So that might have been a little bit confusing. But all we did was take this number 6 for our acceleration, okay, because that was this, our acceleration, and then we... well, our acceleration is our distance 6 times 2. So see, we just did 6 times 2. That is our acceleration right there. And then we need to multiply it by that distance. That's going to be 3/4 L. All right, let's see what we get. So we have, this is going to be, one of these twos cancel. Mass is 1, length is 1. So we have, this is going to be 0.5. So we got 0.5 right there, plus, let's do this one. We have one of these two cancels, so we're going to have 6. 6 times 3 divided by 4. I'm going to say that's 3 times 3 divided by 2. So that's going to be 9/2. Cool, so we have 9/2. And this is 1/2. Cool. So we're going to have 10/2 here. Alright, sweet. Oh, and then I think I probably messed up again. Not really, but let's just go with it. So, oh, did we get it 100% right too? So this number 5 has to equal this number, which we said is 10/2, and that's 5. Okay, so we got it right. So we actually stumbled across the right answer. But now let's, holy Toledo. Okay, so now we'll go back and forth, because we said we could get this acceleration. We said that angular acceleration, how I remember this is like if you have radians per second, radians times radius is something normal, that's tangential velocity. Angular acceleration times radius is something normal, that's tangential velocity. It's because, let's take radians. The units on here are radians per second. That's dimensionless. So it's kind of just 1 divided by second. So you actually need to multiply by a length in meters to get meters per second. That gives you that tangential velocity. So radians times radius is something normal as tangential velocity. Same thing with angular acceleration. The units on that are radians per second squared. Looks like you need to multiply by a distance to get meters per second squared, what you would consider angular tangential acceleration. So yeah, angular acceleration times radius, or radians times radius, is something normal. Because this has radians in it, times radius, that gives you that something normal. Alright, so we have this. This is our tangential velocity of 1, tangential velocity of 2. We're going to insert that equation. So let's do it. So we're going to have 1/2 mgl is equal to this equation. It's going to be 1/2 m, and then we're going to put alpha, and then r, the distance out here is going to be 1/4 L, and then we have and then the distance again, so that's also going to be 1/4 L. Okay, next term, plus 1/2 m, and then we're going to substitute this in. We're going to have alpha. Oh, I totally have to make a better movie on this. But anyway, we're going to do it. We're going to kick this out. Okay, so yeah, all I'm doing is putting alpha r into there. So, and then the distance to this point is going to be 3/4 L, but I still need to do the d term. So that's another 3/4 L. Okay, so here you see that we have 1 L on this side, but we have 2 over here. So we can get rid of the halves. Cool. We can get rid of the masses. Cool. And we can get rid of one of the L's. I'll just take the L right off the end. But we still, what do we have? We have G, and we have all of this still. And so so now we have 1/16 here. In this one we have 9/16. So that's going to give us a total of 10/16, and then we have alpha L. That's going to equal G. So now if we want to solve for our angular acceleration, that's going to be 16/10 G divided by L. And 16/10 is just 1.6. So we got 1.6 G divided by L. Oh, and I totally forgot. We already did this one, but yeah, that was a very good check on reality, because I swear we were kind of you know, losing it. So now we're going to do this method again, but just with this x term. So I was fascinated by that, because it really shows you the continuity. You know what I mean? You're trying to say, hey, in 1 second, you know, these things are going to fall. You know, what's the but it relates back to here. This equation works because the torque is the only driving, I should say this. If you drop yourself off a cliff into some water, the force of your mass times this gravity, this is the driving force. This driving force is operating on your mass, and that's going to change its velocity. So F equals ma. And this is also where it gets confusing. This is like at the most basic, you're just like, well, the force on you when you jump off a cliff is that Fg. It is this this gravitational equation. So that goes into that side. So we have mg over here is equal to your mass times the acceleration that we're trying to find. And sure, it just happens to be that your acceleration is g. Holy hell, it's like, why did I even go down that route? What I wanted to show is that, yeah, in a linear way, if you have a force, that's going to cause motion. But same thing with torque. If you have a torque, that's going to also cause motion, because you still have a force, but now it's kind of being applied over a distance. You're actually getting leverage out of that force, and so you're getting a value on it. And that's why we went to the simplest scenario, a massless rod and the mass on the end. Your torque is going to be mgl, and that's going to equal, in a linear terms, mad. D is equal to L, and your acceleration here is equal to G. But in any other case where you have masses in between, and you have to use continuity. But the driving number on this still stays the same. Well, I mean, you would identify the masses and you would identify the torque, but the number on the torque is the only thing that can drive motion. And I kind of use that philosophy a lot. Is like this one, let's flip this over. This is a very good example. One is it does the teeter-totter. You have someone that weighs 150 and then someone weighs 50. So this is kilograms, so you could say that the mg is going to be 500. You know what I mean? That's going to be mg. This is their mass in kilograms, and then this was going to be 1,500. Okay, sweet. So this is identical to a pulley system where you have 150 and 50, like right at the start. Now, once you get like certain angles, I mean, if this is going to be down here, well, now it's in equilibrium, and then any other angle is going to be a little bit different. But right off the bat, if you let this system go, this teeter-totter with two different people, and this has got to be centered. Sorry if you don't see that. This is L divided by 2. Okay, so this is going to be synonymous with a pulley. And then here, I mean, the reason I'm bringing this up, because I'm going to bring up the term like driving force. Cool. So right here we have a force. Right here is going to be that mg. Is going to be that 1,500. Here we have 500. And so, and this is going to pull down. So our net driving force on this is going to be 1,500 minus 500. Hey, that's going to be 1,000. So we're going to get 1,000 newtons of driving force. But this is the thing on pulleys, is that driving force is on both masses. So if we go to force is equal to mass times acceleration, we found the driving force. That's going to be 1,000 newtons. But our mass is adding these. It's going to be 150 kilograms, and we want to know our acceleration. So in this, our acceleration is going to be 1,000 divided by 150, and we get 1,000 divided by 150. So our acceleration right here is 6.6. So we're not falling like free fall. If we just jumped our 150 kilogram body off a cliff, hell yeah, our acceleration would be g. Our acceleration would be 10. But if we have something kind of resisting that that force that's pulling us to the water, then yeah, our acceleration is going to be less. And in this case, so that was just kind of showing you, like, hey, if you can figure out driving force, and that force is driving on both of those masses, that's the same thing as like driving torque. If you have the driving torque, I'm not going to spell it, but if you have the driving torque and that's operating on both those masses, that is what's going to cause motion. Alright, hell yeah. So now we're going to do a scenario where we're going to split this up. What's the easiest way to split this up? Well, yeah, let's split it up into thirds, just so we don't think there's anything funky going on. So we're going to put the three masses right there, and we have L divided by 6. And we're just going to kind of go for it. We're going to say, hey, look at this. In 1 second, this bar is going to be down here. And we know that this distance right there is x. We know that this distance right here, if this is x, we have 1, 2, 3 segments. This is going to be 3x. 1, 2, 3, 4, 5. This is going to be 5x. All right, hell yeah. Let's do our sum of the moments is equal to MAD, just kind of in a linear way. Moments are force times distance. And we have 1/3 the mass right here. So the force on these is going to be 1/3 mg. So I guess I'll write those Sweet. All right, let's do the first one. So we have the force is 1/3 mg. The distance is 1/6 L. Okay, the next one, plus we have a force of 1/3 mg times the distance of, and let's throw these distances in. All right, we got them. 1, 2, 3, 4, 5, 6. So we have 3 of these 6s to this distance, and we have 5 of those 6s to that distance. So this one is going to be the force, 1/2 mg, times the distance is 3/6 L. All right, next one is 1/3 mg, 5/6 L. All right, but now we're just going to go for it. We know that, hey, this part is going to be ma1 times the distance, plus ma2 times the distance, plus ma3 times the distance. And we just know that A1 is not equal to A2 is not equal to A3, and they're for sure not equal to gravity. Like, maybe one of these is falling at gravity. Who knows? Who cares? But we just know that, hey, this side is not accelerating at all. This side is going hella. All right, so let's do that. And then, but we're going to do our equation. We know that that acceleration term is going to be 2 times the distance term. So for 1, it's going to be 2x. For this one, it's going to be 6x, and for this one, it's going to be 10x. You know what I mean? Or you could say it's going to be 3x times 2. This one's going to be 5x times 2, and you could say that this is just x times 2. You know, so if you want it if you want to kind of keep track of what we're doing, cool. And once we do that, we can solve for x. We'll basically have an equation where we're going to get a number on this side, and then it has to match the number on this side, and our only variable is x. So let's set that up. So this side's going to be MAD, so we have 1/3 m. The acceleration right here is x times 2. So I'm just going to use that form. So we have x times 2, and then the distance is going to be, I guess I'll do that. The distance to this one is going to be 1/6 L. All right, we're done with that term. So now we go to this term. We have 1/3 m. Our acceleration is going to be 3x times 2. And our distance out here is going to be 3/6 L. Cool. All right, last one. We have 1/3 m. Our acceleration on this is going to be 5x times 2, and our distance out to this one is 5/6 L. Cool. And yesterday I put the 2 in front because, you know, if you do this 3, the 3, you see that we have 2 3s right there. We got 2 5s. I guess it really doesn't matter, but, you know, similar terms, we have a 1/3 mg on all these. And then so we're going to have 1/6 plus 3/6 plus 5/6. The 1 and the 5 add up to 6/6. That's a 1, and then this is 1.5. So we have oh, it seems like we get more torque out of the deal. Shouldn't this number still be 5? One-third m, and then all right, holy Toledo, I'm losing my mind, because we want this to be representative of, you know, the typical problem where we just have the center of mass in the middle, and then the torque is equal to mg times 1/2 L. And then so the general form of torque would be mg 1/2 L, and that would be 1 times 10 times 1/2 times 1, and that would be 5. So this number shouldn't change, and yeah, so we're going to have 1.5 over here, but we're going to get a third. So we're going to get a third times, we have 5, 6, 7, 8, 9, 9, 6. And then right here, you know, one of these 3's cancel, and then we get, what? No, I'm doing this wrong. What? Oh, no, and I'm doing this right. Yeah, so we get a half right here, but then we'd multiply it by g, and that'd be 10. That's going to give us the 5. So, holy hell. So let's write this out. We're going to have 1/3 times, then these add up to 9/6 mgl. This is going to be the same as 1/3 times 3 times 3 divided by 6, so that's going to be 1/2. So this term becomes 1/2 mgl, and that's what we've had all along. Alright, hell yeah. So now, yeah, let's do it. So this is going to be, man, well, 6 times 3 is 18, so we're going to have 2/18 mxl plus, this one is going to be 18, and we're going to have 9/18, so we're going to have 18/18 mxl. This one, we're going to have 3 times 6 is 18 on the bottom, and we're going to have 25 times 2. That's going to be 50 mxl. So now we're going to have 20 plus 50. So we're going to have 70/18 mxl is equal to 1/2 mgl. And shouldn't we have two L terms on this? Yeah, I always mess that up. No, we don't, because this x term is yeah. So our units are the same on this. We have mass and then two lengths, mass. Yeah, no, I'm satisfied with that. Hopefully we didn't mess up. And so we have mgl right here. Oh, and then we have mxl. You know what? I think the units on these are the same, but this x is representative of that acceleration. You know what I mean? We're trying to find that acceleration in terms of x. Cool. All right, so I'm just going to simplify this. mgl is equal. I'm going to bring the 2 up here, and that's going to be 70/9. Is that right? Yeah, 70/9 mxl. So we're going to see that we're going to have g is equal to 70/9 x, and we're going to have 10 times 9 divided by 70 is equal to x, which is going to be 90 divided by 70, 9/7. Alright, so 9 divided by 7 is x, and we're going to store that as x. Alright, now we're going to throw it back into the equation. I don't even know if I did it right. So we're going to do 1/3. Mass is 1, length is 1. So we're going to have 1/3 x times 2 times 1/6 plus 1/3 times 3x 2 times 3/6 plus 1/3 5x 2 times 5/6. All right, hell yeah. So that does it. So 5 is equal to 5. All right, so that is our value for our x term. And now that we know that, shouldn't we know something else? Well, yeah, it kind of goes back to the definition of angular acceleration is tangential acceleration divided by the radius. I would rather think it like this. Angular acceleration times radius, or radians times radius, is something normal. That's tangential velocity. And so so these values are a check on reality. So this is my acceleration at that point. So we know, because we solve for x, that now all our accelerations, you know, are work out. So our acceleration right at this point at 1/6 L is 1.285. And oh, and I dropped the gravity term here. Holy Toledo. So yeah, my bad. So let's gravity is equal to 70/9. Oh no, we incorporated the gravity term in. Yeah, so we know that x is yeah, we solve for x. Oh, and we know that our acceleration at this point is 2x. Yeah, our equation for acceleration is 2x at that point. So 2x. So our acceleration, yeah, it is tripping my mind out. But yeah, there you go. So our acceleration is 2.57 meters per second squared. This is our tangential acceleration at a distance of 1/6 L. So if we wanted to know angular acceleration, let's just write angular acceleration times a radius is tangential acceleration. Or it's angular acceleration times that distance is the acceleration tangential at that distance. So what we're saying is our distance is 1/6 L. And our angular acceleration is this, so we should be able to solve for our angular acceleration. That's going to be our tangential acceleration divided by that distance to that point. Tangential acceleration divided by 1/6 L. And so we're going to have this 2.57 divided by 1/6. And we get an angular acceleration of 15.4 radians per second squared divided by the length. And I don't even know if that feels totally wrong. Alright, whoops, I kind of caught my error because we were trying to find this distance x in terms of g, and so x in terms of g would be 9/70 times g, and then our acceleration, our tangential acceleration is going to be double this, so that's going to be 18/70 g, and then our angular acceleration is this divided by L, so that's going to be tangential divided by our radius, or that distance to that, so we're going to have 18/70 g divided by 1/6 L. So now we have 18/70 times 6 g divided by L, and we get 18 times 6 divided by 70, and we get 1.54 g divided by L. And is that a closer approximation than we had before? So here we had 1.6. Yeah, 8/5. So when we just had two little chunks, we had so when we had two little chunks, we got 1.6. And so now we're getting 1.54. And what we're going to see is that we're approaching 1.5. Alright, hell yeah. So so this method works pretty good. No, I'm done with this. This is how I started yesterday. I was just like, well, if I know the distances, then I can figure out the accelerations. But it was just so fascinating that that wasn't the easiest way. But if it wasn't for doing this, then I wouldn't have stumbled across the actual equation to use. And alright, I'm totally bummed I lost a lot of footage. But yeah, so let's just clean this up. So when we solve for x, we actually threw in gravity as 10. So that's where that 15 came from. But let's just solve this term so x is going to be 9/70 9/70 g. So there you go. So x is 9/70 g. And we know that x is this distance. The acceleration is going to be twice that. So the acceleration is going to be 18/70 g. And then shouldn't there be a divided by L in there? Oh yeah, man, I lost so much footage. But yeah, so the acceleration is going to be twice that. So let's just get that. So we have 9 divided by, so we have the acceleration is going to be 18/70 g. This is going to be our tangential acceleration. We have to go back to the equation of what is angular acceleration. It's radians times radius is something normal. And so, angular acceleration is going to be tangential acceleration divided by that distance. So we're saying that this is the acceleration at this point. The distance is 1/6 L. So we're going to have this divided by 1/6 L. And we're going to have 18 divided by 70 divided by 1/6. Cool. So that gives us angular acceleration of 1.54 g divided by L. And that was, so if we go back to just having 2 masses, this had 3 masses. Here we thought our angular acceleration is 1.6 g divided by L right here. And so now we're getting a closer approximation of 1.54. But man, so we lost a lot, but we're going to divvy this up into 4 chunks. And so let me just do it in 4 chunks, and then we'll go and then we'll do it. So yeah, let me just walk you through here, and then we'll do one more, and we'll do 16 chunks. But yeah, so I lost so much footage, kind of bummed. But we're going to divvy this mass up into 4 chunks, and they're each going to be 1/8 away. And so we're going to use our moment equation that says sum of each of these individual moments of the masses is going to equal kind of the linear mass times acceleration and the distance away of all the different particles. But we do have a constraint that the acceleration has to, kind of has to match, where I guess we just go back to this equation that angular acceleration times radius, this is radians times radius, is something normal. This angular acceleration is, this tangential acceleration of each of these. So if we have these linear accelerations, we know that A1 is not equal to A2, is not equal to A3, is not equal to A4, and for sure it's not equal to gravity. Like this is not moving at all, and this is moving faster than gravity. We kind of know that from experimentation. But each of these accelerations, alright, hell yeah. But each of these accelerations have to have the same omega, the same angular acceleration, because they're all connected. So they have the same angular speed and they have the same angular acceleration. And so we throw in that term, whether it's so it's angular acceleration times the distance to that one. So I could say it's distance 1, but then we have a distance 1 again. So we're going to have that term squared. So so this side, you have 1/4 mass times gravity times the distance to them for the torque, and then we can just kind of sum those distance. So this is going to be, if you did them individually, we'd have 1/4 mg, that's the force on this. The distance is 1/8 L away. And then we're going to add it to 1/4 mg. The distance on that one is 1/2 3/8 L away. And then we're going to add this one. It's going to be 1/4 mg is the force, and then the distance is going to be 5/8 L. And then that's kind of how I did this. You have 1 plus 7 is 8/8. This is another 8/8, so we're going to have, this is going to be 16 divided by 8 is 2. 2 times 2 divided by 4 is that 1/2 ml, so we still have the same amount of torque in this configuration, so we're good there. That's going to equal this side, so we have that 1/4 mass. The angular acceleration times the distance is 1/8 L. We're going to have that term squared though, 1/8 L times 1/8 L. This term is going to be that 1/4 mass, angular acceleration of this, times the distance to it squared, and so forth. And so, I guess how did I simplify this? Well, I'm going to, in each of these, I'm going to have a 1/4 m, in each of those, so I'm going to factor that out. I'm going to have an alpha and an L squared, so that's kind of what I factored out. On the bottom of these, I'm going to have a 64, so I factored that out. And then I'm just going to have 1 plus 3 times 3 is 9, 5 times 5 is 25, plus 7 times 7 is 49. Cool. So I'm going to have 84 divided by 64. And so yeah, so I have 84 divided by 64. I still have that 1/4 right here. And then we have alpha L squared. And that's going to equal 1/2 mgl. I can factor out, and I should have a mass in here. Sorry, I kind of dropped the mass. But we can factor out the m and the l. We still have an l over here though. And so and I kind of wanted to do this. I wanted to, use my skills to like, hey, let's simplify this. So I took 84, divided that by 2. That's 42. Divided that by 2 again, it's 21. All right, heck yeah. So I have a 2, this original 2, and then I divided this one by 2 twice. So 1, 2, and then I got 21. So that's what I have up there. This one is 2 times 2. And then I'm going to divide this by 2. So I'm going to have 2 divided by 64. I can't divide this by 2 again, and this doesn't factor by 3. So I have, oh, and did I even write this in? No, I changed this to 27. Whoops. So this is 21/32. Good, I caught an error. And so that's that term right, that's all that term right there. So we have 21/32. And we have alpha L is equal to G, and I'm going to solve for alpha. So that's going to be 32 divided by 21. Yeah, I kind of wrote that wrong. So 32 up top, 21. And then we have, what do we got? Solve for alpha, so then I'm going to divide by L. So we have G divided by L. So we have 32 divided by 21 is alpha is 1.524. So now we're approaching 1.5. So we're getting a better and more accurate answer. All right, sweet. So let's do this one more time and use 8 masses. So we're going to divvy it up into 4s and then again into 8s, and now we're going to put the masses right there. So each of these masses are 1/8 m of the total mass. The distances are going to be 1/16, and so we just have to see that this is 1, 2, this is 3/16. This is 5/16, that's the distance. 5, 7, 9, 11, 13, and 15. Those are the distance out to each of those masses. We're going to sum the moments is equal to the linear, kind of the sum of the linear accelerations of each of those masses. But then our constraint is that angular acceleration times the distance to those masses is equal to tangential velocity. So we can say, is equal to tangential acceleration. So this acceleration right there, A, is equal to angular acceleration times that distance. So let's just write that in. So it's going to be the sum of the mass times angular acceleration times the distance squared. Okay, heck yeah. And then so now this is good for me because now I'm actually seeing the term. So this term right here is the definition of mass moment of inertia. It's mass times distance squared. Cool. And I'm glad I'm doing this because this is the way I like to learn, and I think it's useful for other people, is to take something like a complicated problem. It's kind of like taking an integral problem, where you have masses at each of these little slices that are generating torques, because even to do that, even to say that the mass is in the center and it's generating that much torque, you still would have to use, I don't know if you'd have to use calculus. You'd probably have to use calculus for that. All right, heck yeah. So now we're just kind of getting a more general equation. We have this, all these torques are going to be that 1/8 mass times gravity times the distance L to them, but that distance L is going to be 1/16, and so I guess I'm just going to divide by a 16 because I'm going to have 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. Okay, heck yeah. And so this is going to be, I see that I have a 16 here, a 16 there, a 16 there, and a 16 there. So I have 1, 2, 3, 4. So I basically have 4 times 16. So these kind of cancel. And then I have 4 divided by 8. Hell yeah. So that's still 1/2 MGL. So we're good there. And now we're going to sum this side. So each of these masses are going to be 1/8. We're going to have the mass. We're going to have the angular acceleration, and then we're going to have the distance to each of these masses, the sum of the distance. So we're going to have n squared. So we can factor out a 16 squared downstairs, and then we can, say this is 1 squared plus 3 squared plus 5 squared plus 7 squared, 9 squared, 11 squared, all the way up to 15 squared. Okay, heck yeah. So now we have this side. We can, and then we have, this side is L squared. Cool. And so we can factor out an L on both of those. We can factor out a mass. So just to clean it up, we have 1/2 G is equal to, I'm just going to write the letters, but we have alpha L. And then all the numbers involved on this side. Cool. So I can even get a general, I should do this because, if I'm doing this, I can get a general equation for the next iteration. Why go through this whole process if I can actually see what I'm doing for that next iteration? So we're just going to solve for alpha right now. I'm going to say alpha is 1/2 G divided by L times 16 squared. I guess I have this 1 times 8, I guess. Times 8. And I'm going to, yeah, this is 8 divided by 1, but yeah, times 8 divided by this. And all those terms squared. Okay, sweet. So let me just get this into my calculator. 1 squared plus 3 squared plus 5 squared plus 7 squared, 9 squared, 11, 13, 15. Okay, sweet. I'm going to store that as x. And then we have 16 squared times 8 divided by x times 0.5. So heck yeah. So alpha is 1.506, and we're definitely getting closer to that 1.5. So this is a really good approximation, and it shows you how it's related to linear. And that was kind of cool to kind of end on that, like, hey, I'm actually seeing where that moment of inertia term is coming from. And I don't know, This was kind of, well, I went over it last night and then just made a video on it tonight. So this is one where I should probably clean it up, but honestly, like, kind of making all the mistakes and going through it kind of slowly, and then having those aha moments, because that's the only time that you're going to have an aha moment, is doing something simple and then just throw it on repeat until you actually, it's like the kind of my motto is to, like, hey, use the numbers in the ways, multiply and divide the numbers how they make sense to you, and then see why you multiplied those numbers. And if you did multiply and divide numbers in a sequence, like, that literally is an equation. You can actually kind of usually just write one full equation to get, where you are going. So even right here, I basically kind of have an equation for, like, doing an iteration of this. If I wanted to do the next iteration, I would have 1 plus 3 all the way to, if this was 16, you'd have 32, and then I would have 31 squared. So I would have 1 squared to 31 squared. This would be a 16. This would probably be a 32 squared. You know what I mean? And so, Yep, and I'm going to do that. Might as well do that. So we're going to do 1 squared all the way up to 31 squared. I do know that this is up to 15 squared, so I'm going to do, I'm just going to do 16 plus 17, 18, plus 19 squared. Oh, no. It's, sorry, it's 17 plus 19. It's the odd numbers. Plus 21. 23 plus 25 squared plus 27 squared plus 29 squared plus 31 squared. Okay, hell yeah. I'm going to store that as alpha A. So we have alpha A plus X. Sweet, I'm going to store that as alpha C. So we have that term. We're going to say 32 squared times 16 divided by alpha C times 0.5. And booyah. So there you go. So we have our next iteration, 0.5014. And so, yeah, so that's cool. So this is kind of an equation. You could now, have this in a form where it's just like, yeah, for each iteration. And I'm not very good at that, where you're just like, hey, you have I terms and N terms, and you're like summing. But I do know how to do it in a practical sense. And that will help me get better at like reading, when things are summing and then you have N's and I terms, you know what I mean? By actually doing this, by not being afraid to do, an iterative process or do one simple problem. And then, what we did is we started with the mass in the middle, and then we added masses, and then just keep going. And being able to do more than one problem. So being able to do the same problem 10 times in a row, just kind of tweaking one thing at a time. So, all right, hell yeah. So I'm pretty satisfied with this. Thanks for joining me, and that's a video.